Hello, welcome back to another Anarculus production. Today, we're going to be doing some more FRQs featuring tables, which we looked at in chapter 4, and we're going to see how they combine or work together with the concept of accumulation that we've been talking about for the last couple days. So you can find those problems once again on Google Classroom there in the attachment. If you have questions about the video, please let me know. Okay, so we're going to do these problems together fairly quickly, and we'll go from there and see what happens. All right, let's take a look at number one. Number one talks about water that's being pumped into a tank. Okay, and there's a chart that's there. There's a table, and R of T represents the water that's been removed from the tank, the rate at which the water is removed from the tank. So R of T is the rate out. Okay, we have W of T right above it. That is the rate in. Okay, W of T is given as the rate in, and R of T is the rate out. So this is an accumulation problem. It's just that one of the rates happens to be a table. Okay, it says that it's happening on 0 to 8 closed. That may be important at some point. And at time t equals 0, there's 50,000 liters of water in the tank. That's probably also going to be important. All right, let's take a look at letter A, and we'll see how these problems combine with tables and the accumulation. A asks you to estimate R prime 2. So you're given R in that table. To estimate R prime would be the derivative. In this case, the only way to find the derivative is to find the slope. So I want the slope at 2. Closest I can get would be between 3 and 1. So I'm going to calculate R of 3 minus R of 1 over 3 minus 1. Okay, notice the approximation symbol. Your symbol does have to be an approximation. This is an approximation. And then this is equal to whatever you get. If you write equals here, they will take the point. They'll mark it wrong. All right, so if you do that, you just look in the table and pick the numbers out. And you get 950 minus 1190 over 2, which comes out to be negative 120. All right. It says indicate units of measure. So R represents the rate in liters per hour. So this is like the velocity, right? Liters per hour, that's the rate. The derivative of the rate is the acceleration. So the units here must be negative 120 liters per hour squared. Just like for acceleration would be like meters per second squared. Okay? So this is kind of like a PVA concept as well. All right, that takes care of letter A. All done. Let's go on to letter B. Letter B says use a left Riemann sum. So here we go. Left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank over the 8 hours. All right, so if you remember, all right, we just drew anything. Okay, when we did this, starting from 0, you have 1, 3, 6, and 8. And then from the left would be here, across and down, across and down, across and down. 1, 2, 3, 4. Okay, and then you were able to find the area, right? Just base times height, so it's going to be 1 times R of 0. The next area is 2 times R of 1. The next one is, let's see, we have 3 times R of 3. And then finally we have 2 times R of 6. Okay, we add all these together. We will come up with a total of 8,050. Okay, 8,050 is the total. It wants to know if it's an over or an underestimate of the total amount of water removed. So you need to know whether left Riemann sums are over or underestimates. To figure that out, remember, don't look at this picture. You just randomly drew this picture. You didn't make it model the data. You just drew it so that you could try to figure out what the areas were. You have to go back to the scenario. In the scenario, it says that it's decreasing. Okay, since this is decreasing, if you take a left Riemann sum, it's over. Okay, so this is an overestimate, ATE, because R is decreasing. That's all you have to say, no more. Okay, it's an overestimate because R is decreasing. That's it. Say nothing else. Okay, notice we didn't write units. We didn't write units, they didn't ask us for them. They don't ask you for units, you don't have to give them. All right? Okay, that takes care of B. Let's go on to letter C. For letter C, it wants you to use your answer from part B. Well, too bad I erased that. To find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, here we go. So now they want the total amount of water in the tank. So to find the total amount of water in the tank, we have the rate in and the rate out. I want to know the total in and the total out. So I'm given the rate. I got to integrate to find the total. So I'll have to take the 50,000 that are in there to start, plus the integral from 0 to 8 of W of t dt, because that's how much water is being pumped into the tank from 0 to 8. And then I'm going to have to take out the 80/50 that I just wrote in the last part, because that was the amount of water that was removed from the tank. The 80/50 is not an integral. When you integrated in part B, you integrated by finding the left Riemann sum, right? You just added up all the rectangles. It's an approximation. Okay? So you get 80/50 to remove. All right? And if you do that properly, this goes in the calculator, of course, and you're going to come out with 49,786 liters of water. Okay, to the nearest liter, it does ask you to round it. Otherwise, you put 3 decimal places. All right, so there's your accumulation portion there, okay, right there. And then part D is interesting. It says, is there a time when the rate at which water is pumped into the tank is the same as the rate at which the water is removed from the tank? So in part D, they want to know, is W of t ever equal to R of t? That's what they want to know. All right. So it takes a little bit of calculating, but what we can do is this. If we compare the amount of water being pumped in at t equals 0 versus the amount of water that's being taken out at t equals 0, well, the rate at which water is being taken out is pretty easy. 1340 at t equals 0. W of 0, well, how much water is being pumped into the tank? That would be 2,000. So we can see that W of 0 is greater than R of 0. Okay, the rate at which it's being poured in is greater than the rate at which it's being taken out. Now, if we look at W of 8, what happens at the end versus R of 8, let's see what happens here. W of 8, we can find by taking 8 and plugging it into the function, just typing in your calculator, you get 81.524 versus R of 8, which is in the chart, which is 700. So now R of 8 is bigger than W of 8, which means the rate out is bigger than the rate in. Okay? And we also know that these rates, R and W, are differentiable. It tells us that at the top, which means that R and W are continuous. So since R and W are continuous, then and the rate at which water flows in is greater than the rate at which the water flows out at the beginning, but then they've switched by the end, that means at some point, okay, at some time, the rates must have been equal. Does that make sense? I mean, look at it this way. If you got a faucet with water coming out of it, right, and there's the faucet's pouring water into a bucket, and the bucket has a hole in it. okay? The water is flowing out of the bucket at a certain rate. It's also flowing into the bucket at a certain rate. Now, if one is faster than the other for a while, then it switches. Then at some point, they must have been the same. And they must have been equal at some point. So that would be your answer here. So the answer is yes. Okay? Is there a place where the rate at which water is pumped in is the same as the rate at which water is pumped out? The answer is yes. Okay? And all of this can be your explanation. All right? That's a tricky one. It's probably the toughest one that's there. It's worth 2 out of the 9 points. Not too much, but it is certainly tricky. All right? Okay. So let's take a look at the second one now. Same thing, same idea, another table problem. It talks about a pot of tea that cools. Okay. The temperature is modeled by the T, and H of T represents the temperature. Okay. It's not a rate. It's just the temperature of the T. So let's take a look at letter A. This is a little bit more traditional, like we've done in the past. Use the data in the table to approximate the rate at which the temperature of the T is changing at T equals 3.5. So you want to know the rate at which the temperature is changing at 3.5. You want to know H prime of 3.5. H is the temperature, H prime would be the rate. So I can't do that because I got a table, but I can approximate it with H of 5 minus H of 2 over 5 minus 2. And if you do that properly, you'll come out with negative 2.667. Okay. And you're all done. You don't need to put units. You could if you wanted to. It's pretty easy. Remember, H is measured in degrees Celsius, and the bottom is measured in minutes. So this is Celsius per minute. It's the rate. Okay. It's dropping 2.667 degrees Celsius per minute at T equals 3.5 minutes. That would be your explanation if you were asked one. Okay? All right, let's go to letter B. In letter B, it wants you to, using correct units, explain the meaning of 1/10 the integral from 0 to 10 h of t dt in the context of this problem, and then calculate it with a trapezoidal sum. All right, so let's explain it first. So we talked about this earlier in the course, that if you integrate h of t, and h of t is in degrees Celsius, okay, you'll get an answer in units that's degrees Celsius times minutes when you integrate Celsius. You'll get Celsius times minutes because the time is measured in minutes over the 10. But the 10 is minutes, right? So if I cross these out, okay, I get an answer that's degrees Celsius. But, so what is this over 10 though? This over 10 is taking this integral and dividing it into 10 equal pieces. So what this is telling me is it's telling me the average temperature in degrees Celsius of the T over the 10-minute period. Period from T equals 0 to T equals 10 minutes. Okay? And all of this needs to be part of your answer. It says, using correct units, explain what this is in the context of the T. Not, it's an average value problem. In the context of the T, it's the average temperature in degrees Celsius of the T over the 10-minute period from T equals 0 to T equals 10 minutes. All right, so now let's try to do the rest of part B. I'm going to do a trapezoidal sum. Okay, let's try a trapezoidal sum here. So let's see, just draw anything, it doesn't matter. Gotta remember how to do these. We have 0, 2, 5, 9, and 10. So put a point here, across and down, put a point there, across and down, put a point there, across and down. Yeah, a little further, point there, and across the top. 1, 2, 3, 4. Okay. All right, so the area of the first one, the area of a trapezoid, is half the height times the sum of the bases. So it's going to be half the height. Remember, the height is this distance, half of 2 times h of 0 plus h of 2. Next one, half of 3. That's a half of 3, h of 2 plus h 5. Next one, half of 4, h of 5 plus h of 9. And the last one is half of 1, h of 9 plus h of 10. Okay, if I do that, I add these all together, it gives me a total of 529.5. But I don't want to just sum them, find the integral. I want to take the average of it. I want to divide it into 10 equal pieces. If I do that, I get 52.95. Okay, oops, sorry, I can't see that. So you get, I'll do it over here, 52.95. Okay, that is the integral, or 1/10 the integral from 0 to 10, h of t dt. So there's your answer there. Okay, that we've done before, right? We've done it plenty of times. All right. So let's take a look at part D. So part D, at time t equals 0, biscuits with temperature 100 degrees Celsius were removed from an oven. The temperature of the biscuits at time t is modeled by a differentiable function b if it's known that b prime is equal to that equation. Given using the given models at t equals 10, how much cooler are the biscuits than t? Okay. All right. So we're given b prime. B prime must be the rate of the temperature of the biscuits. Okay. The rate of change of the temperature of the biscuits. Because it says the temperature of the biscuits is modeled by B. We're given B prime, that's the rate. So we need to know what the temperature of the biscuits are at t equals 10. Now, we can figure that out. Okay? We're given the rate. If we integrate, we get the change in temperature. So let's take 100 plus the integral from 0 to 10. B prime t dt. If we do that, we get 34.18275. Okay, so this is the temperature of the biscuits at t equals 10. Now, how much cooler are the biscuits than the t? The t has a temperature of h of 10, right? Using the table. In the table, it says the temperature is 43 degrees. This is for the t. So if I take 43 and just subtract 34.18275, I'll come out with 8.817. Again, round to 3 places after the decimal. And that's how much cooler the biscuits are than the t, 8.817 degrees Celsius. Okay? All right. So I forgot letter C. I think I need to go watch some Sesame Street here after this is over and learn my ABCs again. So let me go back to letter C here real quick before we finish this up. It asks you to evaluate from 0 to 10 h prime of t dt. Okay, and using correct units, explain the meaning of the expression in the context of this problem. Well, we can do this actually pretty easy. The integral of h prime is straight line from 0 to 10 h of t. And I can evaluate that by doing h of 10 minus h of 0. So h of 10 is 43. H of 0 is 66. So that is a total of negative 23. Okay. And now to explain what this is, I took h of 10, the temperature of the t at 10, and subtracted the temperature of the t at 0. It came out to be negative 23. So what does that mean for us in terms of the t? It means the temperature of the t has dropped or decreased 23 degrees Celsius. It asks for the units. You need to give units. Okay, 23 degrees Celsius from time t equals 0 to t equals 10 minutes. When you write your explanation, the bounds matter. The 0 and 10 have to be included. This number has to be included. Do not say the temperature of the T has dropped negative 23 degrees Celsius, because then you're saying that the temperature of the T increased. It went down by negative 23. That means it's positive. Okay? So the temperature of the T has dropped. That's what the negative is. 23 degrees Celsius from time t equals 0 to t equals 10 minutes. You need the two bounds in your explanation, as well as this 23, and how the negative relates to that in this context. Okay? All right, so that's a review and a couple extra things on tables with accumulation. Okay, try the problems for homework, and we'll have a discussion and see how it's going tomorrow. Thanks for clicking.